Davission and German experiment. This experiment for the first time proved the wave nature of electrons and verified the de Broglie equation. In this experiment, we'll study the scattering of electrons by a nickel crystal. This is the target material. The experimental setup for the Davission and Germer experiment is enclosed within a vacuum chamber. Thus, the scattering of electrons by the medium are prevented. Coming to the main parts of the experimental setup, it is the electron gun, static particle accelerator, collimator, target that is a nickel crystal, and the detector. Electron gun. An electron gun is a tungsten filament that emits electrons when heated to a particular temperature. Electrostatic particle accelerator. Two opposite charged particles, either positive and negative plates, are used to accelerate the electrons at a known potential. Coming to the collimator, the accelerator is enclosed within a cylinder. Its function is to render a narrow and straight beam of electrons ready for acceleration. Target. The target in this experimental setup is a nickel crystal. The electron beam is fired normally on the nickel crystal. The crystal is placed in such a way that it can be rotated about a fixed axis. Detector. A detector is used to capture the scattered electrons from the nickel crystal. The detector can be moved in a semicircular arc as shown in this diagram. Here, uh, the inclined angle between the detector and the electron beam is called the scattered angle. It is indicated by theta. And this is the next target. Sir?
Try to make it full screen, okay? Appudu clarity ఉంటుంది. Yeah.
Yes.
Slide show, కింద slide show.
Yes, sir.
Right, okay.
Yes. And this is the nickel target, and this is the inclined angle between the movable detector and the electron beam of light. And the basic thought behind the Davission and Germer experiment was that the waves reflected from two different atomic layers of a nickel crystal will have a fixed phase difference. After reflection, these waves will interfere either constructively or destructively. Therefore, it will have a diffraction splitting pattern. In the Davission Germer experiment, waves were used in place of electrons. These electrons formed a diffraction pattern. The dual nature of matter was thus verified. We can relate de Broglie's equation and Bragg's law for the experiment. From de Broglie's equation, it is known that wavelength equals to Planck's constant by momentum. It is also known that from the kinetic energy, we have kinetic energy equals to half mv square. Here mv is the momentum. On substituting the equations, we get momentum is equals to root over 2m e. Here kinetic energy can also be equated to electron volts. So finally we get lambda equals to h by 2 root over 2m electron volts. This is the de Broglie equation. And coming to the Bragg's law, we have n lambda equals to 2d sine 90 degrees minus theta by 2. Here theta is the scattering. Theta is the angle between the detector uh, and the detector and the nickel target. And since the value of d was already known from the X-ray diffraction experiments, hence for various values of theta, we get various values of lambda. We can find the wavelength of waves producing diffraction pattern from the equation, from the Bragg's equation. Coming to the results of Davission and Germer experiment, in this experiment we get a scattering angle theta and a corresponding value for the wavelength lambda, and we'll get two different values for the lambda. These two values establish the relation between these two values establish the de Broglie's wave particle duality and the equation. And coming to this equation, on using the de Broglie's relation, we get the wavelength as 0.167 nanometers. And in the Bragg's equation, on taking the angle as 50 degrees, we get the wavelength as 0.165. Therefore, the experimental results are in a close agreement with the theoretical values got by the de Broglie equation. Therefore, we have the equations 3 and 4 verify the de Broglie's equation. This is Davission and German experiment.